Hi everybody, Mr. Record here, and we are going to be taking a look at a video here that deals with the integration of the not so pretty trigonometric words like tangent of x, secant of x, cosecant of x, and cotangent of x. And in just a minute I will actually show you an analytic way to find the two integrals that you see here, tangent and secant. But first, I want to go back and kind of remind you, if you're watching this video, it's probably likely that you've already been exposed to what we know to be the 6 basic trig antiderivatives. And you do need to memorize these. It's extremely important to be an effective calculus student, but I don't really think that you have all as that much work to do than what some of you might think. For instance, if we were to look at, say, this guy right here, the integration or the antiderivative of secant squared of x with respect to x, that answer is indeed tangent of x plus c. But if you think about it in reverse, you've already learned from your differential calculus that the derivative of tangent of x is equal to the secant of x. So all you need to do, secant squared of x. So all you need to do is just to apply that in reverse. You would put your integration symbol in front of this guy, secant squared, and we know that that would spit out the answer tangent of x. And of course you have to remember on your own to add the constant c. So if you know the 6 basic trigonometric derivatives, there's really no excuse why you wouldn't know these 6 antiderivatives. Now I know there's some funny things happening with the signs with these things, and that's a pretty easy thing to memorize, because if you were to take the integral of something that's trigonometric, and let's say that the answer starts with the letter C, as you see in these 3 instances, what do you notice about the sign, S-I-G-N, of each of the answers? They are negative. And that's going to be a really helpful memory device to really get these things memorized in a 100% fashion where you can never ever go wrong with them. Now, what about the other basic trig integrals? You'll notice that this chart here, or this table, says nothing about the integration of tangent or secant or cosecant or cotangent. Yes, they do have formulas. They're a little bit more intimidating looking, as you'll see here in a moment at the end of this video, but there are analytic ways that you can solve for these integrals, and I want to show you that first. For example 6a, in the case of the integration of tangent of x, I'm going to do something with tangent of x that many of you would have probably done with tangent of x in a trig class, and that would be to change it to the sine of x over the cosine of x. Sometimes it's easier to work with sine and cosine than it is with tangent. Now, where does that lead us? Well, we're going to end up using a very powerful rule in integral calculus that says that the integration of a 1 over x with respect to x is the natural log of the absolute value of x plus c, or say the chain rule, or general power rule I should say version, is the integration of 1 over u where du dx is present with respect to x is equal to the natural log of the absolute value of u plus c. All right. Now, if you think about this thing, if these dx's were to cancel away, you're just dealing with a integration of du over u. And I think that's what's going to be happening here. It's just that we have to come up with this value of u, this substitution. And given the fact that u seems to be located here in the denominator, it's probably likely that u is going to be the denominator. So let's give it a try. If u is the cosine of x, and we take the derivative of that u with respect to x, we would get negative sine of x. And I've elected to not put the over dx here on the left side, but I'm just going to swing it over here to the right. And we notice something very special. We notice that our original problem had a sine of x times dx in the numerator, and that's exactly what we have in our du expression. So we could almost replace sine of x dx with du. The problem is this guy, this negative. So we have to account for him, and we will account for him simply by bringing him out in front of the integral and then making that replacement. Sine of x dx is du, and then all divided by cosine is all divided by u now. And at which point we can use the formula that is mentioned at the top of the screen. Negative natural log of the absolute value of u plus c, which then means that we could back substitute our cosine in for u. And this would be your most common answer for the integration of the tangent of x with respect to x. I do want to make a little mention about the fact that there are times when I have seen, say, in multiple choice type of problems where the author of the question might decide to take this -1 coefficient in front of the log and move it into the exponent position of what you're taking the logarithm of. If you remember, that's a legal maneuver algebraically. Well, if we do that, notice that we're going to have something along the lines of cosine of x all raised to the -1. Actually, it would be the absolute value of cosine of x to the -1, but I don't really care so much about the absolute value as I do the fact that 1 over cosine of x you know to be equal to the secant of x, hopefully. So that being said, it is highly likely that you could rewrite this as the natural log of the absolute value of the secant of x. It's not done very often, but I wanted to throw that out there just to make sure that nothing in the future surprised you. So there you go. That's a possible answer there for the integration of tangent of x. Now, if you're going to work on the integration of secant of x analytically, it's a little bit weirder. Because if you were to rewrite secant of x as 1 over cosine, it's true. That's exactly what the secant of x is. But 1 over cosine just won't set you up for a very useful application of this guy up here. So instead, we're going to do one of those things that sometimes happens in math classes, and that's pulling a trick just right out of the air, and we're going to multiply the secant of x by something very special. Secant of x plus tangent of x over itself. Yep, I can tell what you're thinking. You don't like that. It is a strange step. However, it's a legal step because we are essentially just multiplying by something that's equivalent to 1. But the motivation behind this is so that we can now let our u be the denominator, secant plus tangent, and hope that its derivative will match the numerator. And sure enough, it will do that because the derivative of the secant of x is secant of x times tangent of x, and the derivative of tangent of x is secant squared of x. And then I'm going to move my dx over as usual, and you will notice, once again, in yellow, the numerator of this original problem, and you might have to think about that secant of x in front as multiplying or distributing through here. You will have the exact same result. Secant times secant matches the secant squared right here, and secant times tangent will be your secant tangent there. And then, of course, they both have a dx. So we have now maneuvered ourselves into a position where we can say that this is nothing more than a big old du on top of secant plus tangent, which was our u, which then, of course, means we have the natural log of the absolute value of u plus c, and then we finish off back substituting in for u. And this would be our answer. It's not pretty, I'll give you that, but the good thing is there's typically no other way that you would present this natural log like you would have, say, in example A. Now, most of the time when I teach this to my students, they're going to all say, well, I don't want to do that, and I agree 100% with them. So what's best is just to memorize it. And here you see on this last slide a listing of the 6 basic trigonometric functions integrals. Yes, it has the 2 that you've already learned, the 2 that are already present, say in the first box that I showed you. But then you see the 2 that I just did here, tangent and secant. And then the cotangent and cosecant work very, very similarly. In fact, if you were to use an analytic means of finding these 2 integrals, it would look very similar to the 2 that I just shown you. A lot of textbooks leave those as exercises. As far as memorization, I do have 2 things that I can share with you. First of all, for the secant, the integration of secant having the words secant and tangent in it, as a student, I always memorized the fact that, okay, the derivative of secant I knew was equal to secant times tangent. So the derivative of secant had the words secant and tangent in it. We'll note that the integral of secant also has the words secant and tangent in it. However, you've got to remember that it's a totally different operator, a plus as opposed to a times. And then, of course, you're on your own in terms of knowing that it has a natural log and the absolute values as well. You can apply the same reasoning here for the cosecant. As far as the sign, S-I-G-N, well, if I get rid of all this stuff, if you look, once again, whenever you take the integral of a trig word, if the answer starts with a C, if the trig word in the answer starts with C, because I know you're thinking, oh, these 2 start with an L for natural log. But let's say if the trig words start with C, once again, you can rely on the fact that your results will always be negative. And I hope that those are some things that you can use to help memorize. The bottom line is that there's no substitute for memorizing these words, these trigonometric integrals and the derivatives. And I find that students who take the time to do that tend to be a lot more confident in some of the things that they do in their calculus class. Now, what are the ways that you can memorize these? Well, one is certainly to make a set of flashcards, take some 3x5s, and just write the formula integral on the front side and write the answer on the back side. Of course, you can use other kinds of electronic flashcards. I know that there's some things on the internet like Quizlet. In fact, my students all use the TI Inspire calculator, and in the TI Inspire calculator you can basically make notes pages which are kind of like their little Word documents, and they can actually make flashcards using the TI Inspire. What I tell them, for those of you who have a TI Inspire, is let every odd page be a formula, integration of sine of u with respect to u, for example, and then on the even page that follows that, you could write the actual answer, and then you can just study by flipping through the pages on your TI Inspire. But there's a lot of different things that you can do. It just takes a little bit of initiative on your part, and if you do that, you'll be a good calculus student. Anyway, I hope this helps, and I'll see you next time.